let's begin. Concepts for grammars and Chomsky normal form. In this presentation, I'm focusing on the foundations and understanding behind grammars, Chomsky normal form, and, well, these. So expansions, which is starting with the basics, which most of us would have done in MLFCS last semester. If you're doing maths in CS, you might not have done that last time. You'll cover the maths part, but this is the logic part. It's still fairly basic, so it should be all right. Then after that, we're doing grammars. And then context-free grammar. So how does it become context-free? What does that actually mean? Converting a DFA to a CFG, and after that, Chomsky normal form, and then derivations of grammars. So let's begin with expansions. Let's go. So think about an object. So this could be anything. So how is it made? How is it structured? What components might it contain? So an object, any two objects, there's so much that could differentiate one from another. Once again, this is a little bit abstract, but it's starting with basics. So we can use logic to describe the components of an object and how it's structured. Let's take an example of a sandwich. Let's call it S. So this is an example of an object. What components might we say that it contains? So slices of bread, food fillings, marmite. No, let's go with Nutella instead of marmite. So we can say S. And this 2 semicolon equals symbol means expands into. So I'll go through that a little bit later as well. But we can say S expands into BNFB, let's say, for example. So we're taking the order of the letters as the layers of the sandwich. We can say, let's say B stands for a slice of bread, N stands for Nutella, and F might stand for food fillings. Now, if these letters are lowercase, then they're called terminals, which means they can't be expanded. We're able to expand S because it's a capital letter. So that's generally how we use them. What if we want to expand the food fillings into other things as well? Then let's alter it a little bit so that can be expanded. So S expands into BN, capital FB, and capital F expands into those 5 options. So now F is uppercase, just like S. Uppercase letters, we say, are variables, and they can be expanded, as we can see here. Hence, we added the second row of expansions. So with these expansions, there are 5 different types of filling that a sandwich could have. Let's go through what they could be. So H maybe could stand for ham, CS could stand for chicken and sweet corn, sorry, vegetarians. These are how we could form them effectively. S could go to BNFB, which could go to BNHB, because F can go to H. Or the second one, S. Yeah, well, you can see how that works, I think. Yeah, I decided that L stands for laptop. It is physically possible to put a laptop inside a sandwich, especially if it's a Mac, because they're so thin. So, yeah, it might be slightly less than edible, but, it's possible. F is just filling again. Yeah, laptops are crunchy. F can be expanded into 2 Fs, so any filling could be 2 fillings instead, we could say. So in this example, S expands into BNFB, that F expands into 2 Fs, I've decided to expand that again into 2 Fs each, so Bn FFFF, and with 3 of those laptops and 1 of them chicken and sweet corn. It's going to be pretty expensive, but it's a sandwich. If you really want, the 5th option for expanding F is you can expand it back into S, so that the initial S contains another sandwich with its own fillings. You can see the example there. Bread, Nutella, laptop, bread. Laptop's definitely a really good source of iron. Crazy sandwich fillings. I don't know what's happened to humanity. So the variables, terminals, and symbols we used, we had the arrow to start off, and then S, a variable, the expand symbol, and then some terminals and a variable F. So S and F, as we said before, are not terminals. Instead, they are variables because they can be expanded. And this is denoted by them being uppercase. B and N are terminals because they are lowercase, so they can't be expanded. The arrow to the left of S means that it's the starting variable, and we can visualize it by saying the starting variable is the whole and complete object. So S, yes, S is a whole sandwich. It's a whole and complete sandwich. Incredible. So this symbol, semicolon, are they semicolons or normal colons? Yeah, I'm not sure. But yeah, the symbol is a notation for a variable can expand into. And the vertical lines separate each possible expansion of a single variable. You can have an infinitely recursive sandwich, that's right. Could it be finite? I mean, if you have infinite sandwiches, I suppose it's kind of infinite. So Bacchus norm form, as many of you may remember from MRCS last semester, it's called Bacchus norm form, BNF. It shows how a whole and complete object, so the starting variable, can be separated into its components via expansion. There's usually just one starting variable when listing expansions in Bacchus norm form. I mean, theoretically, if we did have 2 starting variables, then we could just create a new starting variable and then have two possible expansions of that as each of the initial starting variables. So that results in just one. So theoretically, there shouldn't really be a list of expansions in BNF with multiple start variables. So there are many applications of it, including in context-free grammars, which we're going to use this notation for. So we could add any number of variables and terminals to make more possibilities of what any of the variables could expand into. But there is one more possibility. What if there was no sandwich? So the empty character, we had these expansions before. So there's a particular character that means something different from non-terminals, from normal terminals. Sorry, this is the empty character, which is denoted by epsilon. It's a terminal that specifically contains nothing. So we've altered our BNF a little bit so that S can now expand into epsilon, as well as BNFB. That's another possibility. And if it did expand into this, then the sandwich would contain nothing, not even slices of bread. How very sad. What if we just wanted the filling, F, to be nothing? What if the bread, the precious bread, the godlike, edible material that we unknowingly worship, is something that we wanted to keep? Then let's add an epsilon to the expansions of F. for example, here f has 6 expansions, one of which is epsilon. So now we can expand f into epsilon. So this allows us to obtain Bn epsilon b, which is equivalent to Bnb because epsilon is just empty. Actually, why might we not need an epsilon in the expansions of f? Can we make the filling empty without adding it? Do you guys want to post in the chat how you think we might be able to make the filling empty without using the f epsilon? Scooby-Doo. F can be S and S can be epsilon. That's correct. So S can expand to epsilon, as you said, which means that there is no sandwich, but the filling could just be another sandwich. So F can expand to a variable that expands to epsilon, as you just said. So because F can expand to S, we can use, we don't actually need to have an epsilon as the expansion of F. So let's move on from that, onto grammars. Let's begin. So using backwards null form to describe a string, let's say. An object can be formatted in BNF similar to describe its components. We saw that on the previous section. Let's say we could have a string, let's call it S as well as the sandwich. We're moving on from the sandwich. Let's go for the string. S expands into it will Hux, the sandwich will always contain a teller because the options are Bn Fb. But yes, you have the right idea. So an object can be formatted in backwards null form in order to describe its components. We can have a string S as a whole object consisting of some characters from an alphabet, and we denote this alphabet by a sigma. And the characters in the alphabet are the components of the string, effectively. So if S just has one character, then we can use this BNF, let's say. So S can expand into either A or B. So the entire string only has a length of one character. That's kind of boring. It's not really a string at that point. It's just a character. So it should really be able to contain any number of characters. We can modify what we have slightly to incorporate having either no characters or having more characters. So we've added an epsilon, and we've added 2 S's concatenated. So how does this work? It can consist of either a terminal, so that's A or B. It can consist of nothing, so the epsilon, or 2 concatenated strings. Using this, it's possible to make a string of any number and order of A's and B's. So let's see how we can use that. We could expand S into SS, then BS. It kind of is a bit BS. Then we could expand that S into another SS. We could end up with BBA, for example. We could do this for any number and order of A's and B's. What might happen if we expand a single string into 2 strings and then expand one of these strings into an empty character? So we expand S into SS, then one of those S's we just expand into epsilon. We're back to what we started with. Yeah, that's right. So the 2 expansions negated each other. Negations can happen whenever a variable can expand into 2 of itself concatenated, and then one of these expands into epsilon. So this effectively does nothing. It's not an official term, but it does illustrate something about the expansions. It's an interesting mechanic. So let's say we have S expands into A or epsilon or SS. No matter how many A's we want to concatenate, or whatever string we want to create, so that could just be, that can only be a number of A's because A is the only terminal we have. We will never actually need to use the epsilon because it will just negate one of the S to SS expansions. There's not really a scenario where we'll need to use it. Let's say instead of S expanding into 2 S's, it expands into 3 S's. Might we need to use the epsilon? Well, if we wanted to create AA, for example, we would need to use epsilon ones. Because we expand S into, there's no option for two characters on a single expansion, so we'll need to go from S to 3 S's. Then we'll need to expand one of those S's into epsilon to result in 2 S's. So it would be useful if we had S going into 3 expansions, and therefore if S went into 3 or more expansions. I think that's causal values induction, but I'm not sure. So negation will only happen if we expanded 2 of the S's into epsilons in the case of S expanding into 3 initially, which would be that we would be back to what we started with. So if there's an expansion of a variable into 2 of itself, then using epsilon would always cause a negation. That's kind of a rule. Out of interest, can you see a use for epsilon in the case of S expanding into 2 S's? What word might we be able to create using where we would need to use that epsilon? Do you guys have any ideas? Should I reveal it? Okay, so if we wanted to expand S into nothing, then we would need to use epsilon. It is thinking outside the box, really. Like if we don't want a word at all, or we want it to be empty, then even if any use of epsilon would cause a negation, we could use an epsilon on its own to result in the empty word. So this is potentially the only use that epsilon would have in the scenario of negations. As a side note, if we had the expansion, so we talked about S expanding into 2 S's, or S expanding into 3 or more S's. If S expanded into 1 S, then a negation is actually impossible, because any use of epsilon will just go to an empty string, like in total. So in fact, the expansion of S into S is completely useless. A variable expanding into one of itself does nothing at all. I mean, can you imagine S to S to S to S, a continuous cycle for all eternity with no progress whatsoever, back to where we okay, I'm sure you can read that. Yeah, let's move on. So, making a grammar from some alphabets. Previously, we had sigma equals A and B, and we had these expansions. So S can expand to A or B or epsilon or SS. Let's make another alphabet. So let's call that sigma 2. We don't really need to worry about what the name of the alphabet is, only what it contains, really. So if we're adding another alphabet to the possible expansions of S, then we can expand S into AB01 epsilon or SS. So we've added the 0 and 1. We could potentially add as many as we like. So here I've added some operators as well. So we have a lot of single expansions from S, and because of the SS expansion, as we've seen before, we can make a string have an infinite length. It's kind of messy though. Remember before with the sandwich, we had another variable f for the sandwich fillings. So we can introduce as many variables as we like, just like we introduced f before. So let's try introducing one for here. Let's try introducing one for each alphabet. So we can take the terminals a and b out and put it into a variable a, for example, and then we can replace those potential expansions in S with a variable A, and we can do the same with B and C. So S can expand to any of the three variables that list in their expansions their own terminals, their own alphabets, for example. So this is much neater, and the language hasn't changed. So we'll be talking about the language changing in a couple slides, I think. A set of expandable variables like this is what a grammar is. So a grammar is a grammar is a list of or a set of expandable variables in Backus-Naur form. That's what a grammar is. The language is the set of possible words that we can make using grammar. Because we have S can expand into SS, our language is actually infinite, so it's an infinite set. If there exists some loop in the grammar where something can be concatenated on each iteration of the loop, then this means the language will be infinite, because there can be, well, if a variable expands to itself, then there could potentially be an infinite number of those iterations. Hence, if something is concatenated each loop, then there can be an infinite number of concatenations. So if a loop happens when a variable can eventually be expanded into itself again, a loop happens when it can be expanded into itself again. The variable could expand to a different variable, which expands back to the original one. That's also a loop. But yeah, in the hilarious example of S just expanding into one of itself, well, it is an infinite loop, but nothing's concatenated. So actually, although it's an infinite loop, that wouldn't make the language infinite, because the words that's generated just wouldn't change after each iteration. However, if S expands into, let's say, two S's, for example, then each iteration concatenates it with another S. Even if instead of another S, it concatenated with something like a terminal, so S might expand into S terminal A, then every iteration would add another terminal A to the word, so that would be infinite. So now, let's move on from grammars to context-free grammars. Just to warn you, there's no context whatsoever to these grammars, just a warning. What makes it context-free? So we've looked at grammars. What does it actually mean for it to be context-free? A grammar contains variables, terminals, and possibly epsilon, empty terminals. So let's take the grammar used before. So we have variables S, A, B, and C. They have their own expansions. We can have a string of two letters by expanding S into SS, then expanding each S into A and each A into either A or B. So that's how we can get two letters. But hang on, we expanded an S into SS, both S's into A's, but they have the same name. So hang on, they have the same name, but we're treating them like separate variables. Surely, if they have the same name, then they should represent the same thing. Like, we can't have two A's, one of them expanding into terminal A, one of them expanding into terminal B. They have the same name. It's a valid argument, but if this argument was true, then the variables would have context. So a variable A would have the context of a terminal A, for example. So this would mean that anything named A is the same as each other. So A would represent a unique object. We haven't been doing this with any variables in our grammar. If in the grammar we have here, we have two A's, we could expand one of them into A and one of them into B, into terminal B. That would be completely fine. So regardless of whether or not two variables have the same name, we can expand them into each one into any of their expansions. So this is what makes it context-free. The variables do not have context. So that's actually what makes it context-free grammar. So let's see an example of what we can do with it. So here's our CFG, context-free grammar. Currently, it doesn't really make much sense. It's an infinite number of meaningless words, like A0 star plus plus B10 BB minus equals 1A1 minus. The dot is a full stop, it's not included. It's no better than the English language, which is a very shitty language. Let's modify it a bit. So instead of expanding S into SS, which could just make random concatenations of characters from any alphabet, let's make it so that only letters and numbers themselves can be concatenated with themselves into infinite strings. So we've moved SS from S, and we've put concatenations AA into the expansion of A and BB into the expansion of B. So we've removed the SS expansion and instead added A and BB expansions. This would mean that, that numbers can't be concatenated with letters and vice versa, but they could still be infinite, because if a variable expands into two in itself, then it's an infinite loop with a concatenation, as we've said before. We haven't added a CC expansion though, because, well, concatenating several operators wouldn't really make much sense to us. Why should we put AA as an expansion of A, as not S though? So will we still be able to make infinite strings with this? S expanding into AA, and then each of those A's expanding into terminals. Well, this wouldn't make the language infinite, because A needs to expand into itself, as we said before. If there's an expansion of a variable into several of itself, or if there exists some kind of loop in which a loop doesn't exist in the grammar we've just made now, then it won't be infinite. So we could make A expand into S. So currently A can expand into terminals A or B. If we add a possibility to make it S, then this would make a loop. So S could go to AA, which could go to SS. But it's more efficient to make A expand into itself instead. So if we modify, using the context-free grammar at the top of the slide, if we modify the expansion of S, we could make some strings that might have some meaning to us. So we can make infinite concatenations of letters and numbers, for example, or we can just have an operator. Let's remove A for a second, and let's modify it a bit. So S now expands into BCB, or epsilon, and we've kept B and C the same. We've removed A for a second. Let's see, what might we be able to do with this? So if we have BCB, what's an example of what we might be able to create? Do you want to post in the chat? Or I'll just reveal. So we can make things like binary expressions, for example. So 1 0 plus 1 0 1. So B can expand into BB, making us able to form a binary number as an infinite string of zeros and ones. We could, I suppose, alter it a little bit more to to allow us to make mathematical statements. So saying like a number plus a number equals a number, for example. So in order to make those, we'll need number operator, number operator, number operator, number, etc. until the end. B is a number and C is an operator, so we'll need to make something like BC, 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 B, etc. So how can we make it from this? We could expand S into SS, which would allow us to create BCB, 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 etc. It kind of works, but then, well, every number between operators is automatically 2 B's, so each of those numbers would have to be at least two digits or 2 bits, which which would be inconvenient if we wanted them to be a single bit. I suppose yes, we could have a 0 as the first bit, but we're not actually trying to make the maths work at the moment. We're just trying to make a string. We could alter S a little bit. We could expand S into B. We can have possible expansion of S as B and SCB, or the other way around, B and BCS, which could work because we could expand S into SCB continually because it's a loop. There includes an S in SCB, and then finish the string by expanding the final S into B. So we can try that. So here's how I've altered the context-free grammar. Yeah. So we can use this to make, for example, we've used the SCB expansion as a loop. So we can say 1 0 minus 1 plus 1 equals 1 0. So that's a mathematical statement that we can create like this. Yes, we can also make incorrect statements like 0 equals 1. I mean, I've got no idea whether that's true or not at this point. But all we're trying to do is structure the string correctly, which we've done. We don't really care about the maths, just like a true mathematician. So we can probably prove that 0 equals 1, but we're not going to do that. Hang on though. S can expand into epsilon. So if we expand S into SCB, then that S can expand into epsilon, which means that we end up with CB, so operator number. Should we be able to start with an operator? That wouldn't really make much sense. We need to keep the epsilon in case we want the string to be empty. So let's instead alter it a little bit by adding another variable, and instead of altering S like before, we can alter this new variable. So instead of expanding S into SCB, we can expand S into BD, let's say, and then D could expand into operator number. So expanding S into BD could give number operator number, and D also has the expansion into DD, which could mean that we have S expands into BD, so number D, and then an infinite number of D's could be number, operator number, etc. So this could work. So we can now make like the same string as before, 1 0 plus 1 minus 1 equals 1 0, which is a valid string, but there isn't really a way to add an operator to the end or the beginning. So we've resolved the issue from before. Before we had the variable a expanding into letters. yeah, 0 equals 1 could be correct for some definition. That is true. They're not actually numbers, because it's context free, as you say. But yeah, let's try putting a back in. Let's see what we can do with that. Let's also move the equal sign out of the expansions of C. We can put it somewhere else because it operates slightly different to the other operators. So generally we might just want a single equal sign. So we can put it somewhere outside of a loop, for example. So I've changed the expansions of S a little bit. So instead of just saying S expands to BD, I've said S expands into A equals BD. I've also added A equals B. So what might we be able to do with this? Any ideas? You can post in the chat if you want. It's a bit quiet today. There's only 5 of you in the audience. Yeah, it is 11, but yeah. Alright, I'll say what we can do with this. So if we expand S into A equals BD, then we can expand A into however many letters we want, because A can expand to A. So let's call it ABB. And then we have an equals, and then as we had before, number operator, but the operators themselves don't contain equals anymore. As we can see, we've changed C a little bit. So we can say ABB equals mathematical expression using the A equals BD. This is like assigning values to variables in a programming language. So it means that S, the starting variable, the starting CFG variable, not programming language variable, so the starting variable S is the statement, so the entire string, and all the other variables and terminals are the statement's components. We also added A equals B as an expansion of S, as well as A equals BD. What can we do with A equals B that we can't do with A equals BD? Because there's only 5 of you in the audience, I'm gonna just go through questions myself. So using A equals BD, we can assign a single number to a variable instead of an expression. But with A equals BD, well, D can't expand into epsilon, so we need to. So the only thing we can do is say variable equals number, operator number, etc. With A equals BD. But with A equals B, we can just say variable equals number. Alternatively, we could have added epsilon as an expansion of D, which would work as well. But there are multiple ways to do it. It says that right here. There are multiple ways to alter a grammar, but if after altering a grammar, if altering a grammar allows it to make different strings or removes a possible string, I should say a word. So if there's a word that exists, if there exists a word that can be created before or after grammar is altered, but cannot be created the other way around, then it means its language has changed. So the language itself isn't the sigma from before, that's the alphabet, which is a set containing all of the terminals. The language of a grammar is a set of all possible words that can be created. If there exists a word in a grammar's language that doesn't exist after the grammar is altered, then altering the grammar has changed its language. Another scenario could be if there doesn't exist. It could be if there doesn't exist a word that cannot be created after it's altered, but there exist new words that can be created after it's altered. That also changes the language. So we need to be careful of that if we want to avoid changing the language. But sometimes we do want to change the language, like I've been doing with our CFG here. So let's move on to DFAs and context-free grammars. So how do CFGs relate to DFAs? Any kind of language that is formed by a regex or a DFA can be described by some kind of context-free grammar. The language of the context-free grammar contains words or strings that are from the DFA's alphabet. Hang on. Yeah, strings of characters from the DFA's alphabet. That wasn't very clear, sorry. So this means that the starting variable, s, is any complete word that is accepted by the DFA. So when it reaches the accepted, or the enlightened state, as I call it, it's finally reached acceptance, then this is the starting variable. Well, the whole starting variable. The components of S include variables and terminals, which we can create a CFG from that creates the language accepted by the DFA. So let's use this as an example. This DFA. I would ask what possible rejects could we make from this, but there's only 5 of you in the audience, so I'm gonna go through it like this. So rejects could be, we could say A, B, A star, B, because the A star is a loop. I know I haven't named the states, but I think it's optional. It's probably better to name the states in an exam question, but yeah, as I've avoided that here because it's still understandable. Rejects like these can be described by context-free grammar. So this regex has a language AB. So what might a suitable context-free grammar for this regex look like? So we can. Okay, sure. I'll give you a minute when there's a question. Sorry, yeah. Anyway, yeah, I pressed the spacebar without thinking just then. So what might a suitable context-free grammar look like? We could say S expands into terminal A, B, variable A, terminal B, and then A could expand into terminal A or 2 of itself. So this could make an infinite number of terminal A's. So a CFG like this would work. Remember, we need an epsilon as an expansion of A because A star could have a length of 0. So converting a DFA into a CFG. So we've looked at how they relate. So we can have a DFA find its rejects and then analyze the rejects. That's pretty much what we're gonna do. So the characters in the DFA's alphabet are the terminals in the context-free grammar. We can make any number of variables that we want to give some structure to the language, or just to make it neater. So by analyzing the DFA or the rejects and the words that it accepts, the CFG can be visualized and created just like in the previous slide. So a useful method is to create a starting variable in a CFG, then make it's a little bit tedious, but it works. Make each and every accepted word into expansions of the starting variable initially. So this could be the first step. We have 4 possibilities: A, B, 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 A, A, B, B, A, B, B, A, or A, A, B, A, for example, from this regex. So we can make them all expansions of the starting variable. It is a little bit tedious, but we can neaten it up. Also, if there's a loop, actually that's not going to work. So we need to skip the step where we lay everything out in the starting variable. Because as we can see here, we could get an infinite number of A's in the 3rd character. So we do need another variable for this. As we did before, we can say A, B, variable A, terminal B. And then we could have another variable expanding as 2 of itself, which could account for the A star. So then, if we were to say the first rejects, we had A, B or A, B, B or A, we could analyze the expansions or the rejects for patterns. So and then these patterns can be put into more variables. This is similar to what we did with the A star just now. So so there could be a pattern of an infinite number of A's. So we could put that into a new variable, so variable A. So let's see how we can make this neater. We can see from either the rejects or the CFG that the first and third characters are constant. So the first character is always A, and the third character is always B. So what we could do is have this. So we can say A variable A, B variable A, because we know that the first and third characters are going to be A and B, and the second and fourth ones could be any of them. So this is the kind of pattern which we can identify and then introduce variables for. So it can start a bit messy, but pattern analysis and introducing variables can make the CFG neater. You might be able to analyze the patterns of just the rejects before you've made the starting variable, like we had to do with A star. That could save you a few steps, but if you're doing it in your head, make sure it's clear in your head. Otherwise you might accidentally change the language. So let's move on from that now. Chomsky normal form. So I would like to welcome everyone Noam Chomsky himself to join us here today and talk about this normal form of his. I said that I'd like to, because this is how it's usually said, but I couldn't really contact him. It would be funny though. According to the wiki, he is 95 years old, and I can't seem to find anything that says he's dead. He might be, I don't know. So, I asked another very knowledgeable guest to join us here today, but they couldn't make it to the Discord meeting. This was their response. So, yeah. AI bastard. I also clicked bad response at the bottom, because, yeah, the bastard. So, how many concepts for grammars could potentially describe one language? It contains variables and terminals, which, well, yeah, we could theoretically make any number of variables that we want, whilst not changing the language of the context grammar. So if A expands into variable B and then into A, there will be no difference if variable A expands into variable B into variable C into A, for example. We could theoretically continue introducing new variables like this without changing the language at all. So this shows that there are an infinite number of possible CFGs that can describe the language. Adding more, introducing more variables could make it more complex, or it could make it less complex. That's complex according to a computer. At the same time, removing variables and replacing them with their expansions in previous expansions might make the CFG more complex or less complex. There's a specific way of changing the CFG without changing the language in a way that can reduce how complex it is. So this form, so the form taken by the CFG after we've reduced it like this is Chomsky normal form. So there are specific rules that the expansions need to follow and about the structure of the grammar. For some given grammar, variables can be added and removed as we wish in order to follow the Chomsky normal form rules. So the intention is to make it less algorithmically complex. So it's minimize the size of the expansions whilst maximizing the number of expansions. So the first rule. There are three main rules. The first one is epsilon rules. If a variable can expand into epsilon, then this adds nothing to the string. if S expands into A expands into B expands into epsilon, well, this makes the string empty, so why should we have to traverse through all of the variables to find this? Let's just put epsilon as an expansion to the starting variable instead. The language hasn't changed at all, so this is an equivalence context-free grammar, for example. So how do we use the epsilon rule? Let's take this. Let's take this CFG. So S can expand into A or B. You can just about read that. Is the size of the text okay? I think it's the same size as some previous layers. So we don't want to go through several expansions only to find that B text size. All right, cool. So we don't want to go through several expansions only to find that B expands into epsilon. We want to minimize the number of expansions to find an empty string. So should we move the epsilon from B to S? So let's see what would happen in this case. We've removed the epsilon from the expansions of variable B and appended it onto S. So this could work, but it's reduced the number of expansions to find the empty string. But actually, we've changed the language. So before, S could expand into A, which could expand into AB, which could expand into A epsilon, so A was possible. But now, there's not really a way for us to acquire terminal A, so the language has changed a little bit. If there's a word that's accepted before but rejected after we change the context-free grammar, then the language won't be the same. It's not the same. It's so sad. So this has happened because here there's another occurrence of B, which is in the expansion of variable A into AB. So in this case, we could put epsilon into the expansions of A as well. So instead of just having A expands into variables AB, we could add variable A epsilon. So just like we did when we shifted the epsilon to S. So here the language has not changed. So we could also replace all occurrences of B with B's expansions. So instead of just moving the epsilon, we could move the variable B itself. So yeah, for example, in the expansions of S, instead of saying S expands into variable A, variable B, we say variable A, then everything that variable B could expand into, so that's terminal B and epsilon. And we did the same thing with variable A, for example. So the first rule of CNF is that epsilon is only ever expanded to from the starting variable. If there's a variable or a terminal concatenated with epsilon, then of course the epsilon will have no effect, so it can simply be removed without consideration. So in the expansion of A, I've changed A expands to A to A expands to I've changed A expands to A epsilon, so A expands to A. That's completely fine. If there exists an epsilon anywhere in the grammar, then it's always possible to either remove it using some methods or shift it to the starting variable like we just did. Let's take this context-free grammar, because we've been shifting the epsilon to the starting variable, but can it always be shifted there? Can we shift it? Let's try. Remove epsilon. So we're removing epsilon from the expansion of B and replacing all occurrences of B with B's expansion. So we're eliminating B. So now, instead of saying S expands into AB, we're saying S expands into A expansions of B. So AA or A epsilon or A. So that's is simplified to A epsilon simplifies to A. So with this, we've eliminated. So with this, there isn't an epsilon in this context of grammar. We've eliminated it instead of shifting it. It's still perfectly fine because we haven't changed the language, unless I've made a mistake somewhere, but I don't think I have. So as long as the language hasn't changed as we're converting CFG into Chomsky normal form, then that'll be fine. The epsilon might be eliminated instead of shifted. So should we? So in order to shift epsilon or to remove epsilon, should we always eliminate a variable? Ah, yeah. Sometimes it's useful to create a new starting variable as well. So let's take this. Let's take this context-free grammar. We can create a new starting variable and expand it into S. So at the top we have S expands into A, B, or A, C, or A expands into its expansions, B expands into B and C expand into their own ones. A useful thing to do is to create a new starting variable. So we can call it S0 and just expand it into the initial starting variable for now. So S0 expands into S, then S has its own expansions, etc. So let's start off with C. C has an epsilon. How are we going to? Let's try. Let's try either removing that epsilon or shifting it. So we can eliminate C. Let's see. We have changed S a little bit because it has AC. So we've replaced that with A terminal B or A epsilon, which just equals A terminal B or A. And then A could also expand to C, so we've replaced that with B or epsilon, or A B or A epsilon, or epsilon, which simplifies to B or epsilon or A B or A. And then variable B is unchanged because it could not expand into C. So this shouldn't have changed the language. But now A contains epsilon. So let's see how we could shift that. We could replace the occurrences of A with its expansions. So we could eliminate A, but A has a lot of expansions. It would be very time consuming because 4 possible expansions. The only terminal that we want to shift is epsilon, and that's just one of these 4 expansions. So something we can do is we can duplicate the occurrences of A in the other variables and replace one of these duplicates with epsilon. So in S, S can expand into, it could initially expand into variable A, variable B, variable A, terminal B, etc. So for each of these that includes the variable A, we can duplicate it and then replace the variable A with epsilon, and that's what we've done here. So we've eliminated. Let's see. Have we eliminated it? No, epsilon. Into A, B, or B. Yes, I believe that's correct. But we've eliminated it, so the epsilon rule is being obeyed. But we didn't need to eliminate the variable A itself. Instead, we just duplicated its occurrences. This is another valid way of shifting epsilon. Yeah, so epsilon is being shifted. It's not being. Okay, we've eliminated epsilon from the variable A. I should have said. Sorry, even I got confused at my own wording for a second. So if there exists an epsilon as an expansion of S, then this is where S0 is useful. So we introduce S0, and then epsilon can just be shifted to S0 to maximize the efficiency of finding an empty word. So here we've just shifted epsilon from S to S0, which is relatively easy because S0 is the only thing that can be expanded to S. So now, the second rule of CNF. Second rule states that in a single expansion, terminals must not be concatenated with anything. Let's take the expansion S0 goes to S or epsilon, S goes to ABA or B, and then A and B have their own expansions. So the single expansion variable A goes to terminal B, that's fine because the terminal B isn't concatenated with anything. Single expansion variable A goes to terminals AA is a concatenation of terminals, so we're going to need to alter this. And that's the same with variable B goes to terminal B variable A, so that's a concatenation of a terminal and variable. So the terminal is concatenated with something. So we're going to need to alter that as well. Let's try resolving A goes to terminals AA first. So eliminating A or duplicating its occurrences wouldn't help at all, because then we'd end up with an expansion like S goes to, I don't know, terminals AA, variable B terminals AA. So all that does is just make the terminals more complicated. It doesn't remove the concatenations. It's not very helpful. So instead of eliminating the variables, let's try introducing new variables. So before we had A expands into terminals AA, what if each of those terminals was just a single expansion of a new variable we can introduce? So here I've introduced C. So variable A now expands into variable CC, and C expands into A. I've also introduced D, because that could resolve the variable B goes to terminal B variable A one. So the variables C and D can only be expanded to A and B respectively. We've introduced them and replaced any occurrences of the A and B terminals where they are concatenated. If there were any other concatenations of terminals, we wouldn't need to introduce new variables, because we can just replace their occurrences with C or D again. So this should theoretically mean that the maximum number of variables to introduce would be equal to the size of the alphabet. That's kind of a bit of theory. I mean, theoretically, if you wanted to be pedantic, you could say, oh, everything's a concatenation of epsilon, so terminal A equals A epsilon equals A epsilon epsilon, etc. It would mean that you can't, this would mean that you can't have an unconcatenated terminal. I don't know, I just sound like a politician at this point. So we can pretty much ignore that. Everything is indeed nothing, and nothing is everything. That's the way of life. With the third rule, we've done the first and second rule. The third one is that single expansions into variables can only exist as two concatenated variables. So unit variable expansions and concatenations of three or more variables need to be altered. So we're assuming that we're already obeying the first and second rules of CNF. So because of the second rule, concatenations with terminals already won't exist. So let's take this CFG. So we have an S0. S expands into AAA or AB. Variable A can expand into terminal A or variable B, and then similar with B. So S expands into variables AB is fine, because that's, as we say, a concatenation of two variables. Single expansions A goes to B and B goes to B, they're unit variable expansions, so they don't obey the third rule. We're going to need to alter them. Similarly, we're going to need to alter S expands into AAA. So to start off, B expands into B. No. Remove it. Expanding B into itself without concatenating anything is absolutely useless. So we can just remove that expansion. So removing unit variable expansions, if there's anything that expands to itself, just, fuck it. How should we alter the A goes to B expansion? Could we introduce variables? Could we eliminate variables? So something we could do. What would happen if we try introducing variables? Maybe introducing C, so A goes to C goes to B, but actually this would cause more unit variables, so this unit expansions. So actually this wouldn't help. Concatenating another variable to B could work, so A goes to B, C, but in order for this to not change the language, C would need to go to epsilon. So then the epsilon rule wouldn't be being obeyed. What would happen if we eliminated B? So we can try that. S0 goes to S or epsilon, and then instead of saying S expands into variables A, B, S expands into variable A terminal B. And similar with A now expands into terminal B instead of variable B. So, but now, we've eliminated variable B, but now S expands into variable A terminal B, which doesn't obey the second rule. However, this does have an easy fix. We can introduce B again, just for this terminal concatenation. So if we introduce B again, but we don't change the variable A, the variable A's expansions, then S now expands into variable A, variable B again. So this is one way to do it. We could eliminate unit variables and then reintroduce them for wherever the second rule is broken. There's a logical shortcut which is of doing this, which is instead of eliminating the unit variable and replacing all occurrences, we could leave the unit variable where it is and just replace any unit occurrences of the variable only. So only where it's a unit expansion. So with this, let's now have a look at the S expands into AAA. It's a concatenation of 3 or more variables, so this needs to be altered. Eliminating A won't work, that would just make low terminal concatenations. We could introduce a new variable, so eliminating won't work, introduction could work. So if we were to say C expands into AA, like we've done, we could say S expands into AC, and then C expands into AA. So that would give AAA, and the rules, and the third rule looks like it's being obeyed. So introducing new variables can remove concatenations of 3 variables, for example. How about if we have more than 3 variables? For example, S expands into AAB. So if there's 3 A's, then we introduce C. What might we be able to do with more of them? A 3 and n-3 expansion. Yes, I believe that could work. But for an expansion into 3 variables, we introduce 1 variable. Yes, and then split those until you get a bunch of 2 or less, effectively. That's pretty much correct. So we can effectively iterate the variable introductions, and then we can split those into new variables, just as you said, until we get a bunch of 2 or less. Well, actually, not less than 2, but yeah, exactly 2. But yeah, you have the right idea. So introducing a new variable for each initially concatenated variable is a way to obey it. So we can go along the variables one by one. So AA, so we can change so we can change the ABAB into C, and then the BAB of C into D, and then the AB of D into E, and then the final 2. Now, Chomsky normal form is almost complete, but we forgot about the starting variable. It's a unit variable expansion. Well, we can substitute the expansion of S into S with S expansions, but doesn't this look a little bit messy? We have S0 and S having almost exactly the same expansions. So in this case, what's the point of S0? Surely we can just move the epsilon to S and make S the starting variable again. I mean, there's nothing that even expands to S, and if we were to remove S and then change and then rename S0 to S, the language wouldn't change. Well, imagine if S0 did expand to S. So here I've added an expansion of AS. In this case, if we did replace S0 with S, the starting variable would be able to expand to itself. Any variables after the first expansion are not really considered starting variables, so even if the starting variable did expand once to itself, this new starting variable wouldn't actually be a starting. It wouldn't obey the same rules as the initial starting variable, if you know what I mean. So that means that something that's not really representing a starting variable can expand to epsilon. So theoretically, we would be breaking the epsilon rule. So using this logic, it's best to keep both S0 and S, even if it looks like they're almost identical. Of course, if there's nothing that expands to S, then S is useless. It might be fine to remove it, but it's generally to be able to obey all three rules, then S0 and S should be almost identical, but S0 might or might not have epsilon depending on whether it's eliminated or shifted. Now that's Chomsky normal form complete. Final section, derivations. Let's go. So what's a derivation? It's a way of demonstrating how to create a string from a context-free grammar, expansion by expansion. So let's take this CFG. We have S expands into A or BBA or epsilon, then A and B also have their expansions. It's not in Chomsky normal form, but it's CNF anyway. So the proper name for a character is a token. So for each token in a string, we can derive it using an illustration. Let's take BBABB. So from the above context-free grammar, we might derive it like this. So we would say S at the top expands into terminal B variable A. That variable A can expand into terminal A variable B, etc. until we have a string of terminals. So this means that terminals underneath each consecutive triangle, reading from left to right, are concatenated to form the string. So from left to right, that's effectively going from the leftmost terminal, and then going right until we reach a variable, going up to that's triangle, and then going right until the next variable, etc. until we've formed the entire string. So a single triangle means a single expansion of a variable, and using in like a tree formation like this is the general way to illustrate it. It's also called a parse tree, this kind of structure. Ambiguity. Sometimes there might be multiple derivations of a single string. So let's take this context-free grammar. The string ABAB could be derived via either of these two. So S could expand to variable A, which goes to terminal A variable B, etc. Or S could expand into variable A and variable B, which could have their own sub-parse trees, if you like. So both of these parse trees are different derivations of the same word, ABAB. And because they're different, but they end up with the same word, then there isn't a single definite way. There isn't just a single way to form the word, which means that the grammar is ambiguous. If there exists a single word accepted by context-free grammar that has more than one pass-through for its derivation, then the entire grammar is ambiguous. Strangely, there isn't actually a machine that can prove that it's ambiguous, so it's undecidable. I mean, it should be decidable, in my opinion, but apparently it's undecidable. We don't need to prove that it's undecidable, I believe, unless it's unless it comes up in a question in the undecidability section of TOC. So now derivations leftmost and rightmost. Derivations themselves don't always need to be done via pass-through. Pass-throughs are useful because they're good at illustrating it, but we can use the structure or the theoretical structure of a context-free grammar to derive a word. So it can be described by a tuple of length 4 structured V, sigma, R, and S. So V is a finite set containing all the variables in the context-free grammar. Sigma is a finite set containing the terminals in the context-free grammar, so it's also the alphabet of equivalent reject or DFA. R is a finite set containing all the possible expansions in the CFG. The proper name for these are productions. So an expansion is a production. And finally, S is an element of V. So, oh shit, I didn't put a symbol in. Sorry about that. And it denotes the starting variable. So using the structure, you can show a derivation as a list of productions performed on individual variables in the string. So let's take this context-free grammar. At each step of the derivation, one variable is expanded. So the leftmost and rightmost derivations, well, as the name suggests, they expand the leftmost and rightmost variable respectively. So let's take ABAA as an example. The leftmost and rightmost would be something like this. So leftmost, we expand, so we have S expands into variable A, terminal B, variable A, variable B, and then the leftmost variable of that we expand first, and then the leftmost of what we have left we expand. The leftmost of what we have left we expand until we have the word. Similarly, the rightmost we expand the rightmost variable first at each stage. So this is generally the structure of leftmost and rightmost derivations. The squiggly line arrow is, I don't know why we use it, but it's the general way of denoting these derivations. It's also, common practice to put a small dot above the variable you're going to expand next, but because I would need to create text boxes for all of that, and or use geometry, I can be bothered for that. Yes, I think you're right. I never really thought of that. A pre and post order traversal. I think you're correct. Yes, I'm recording on a different device to the one I'm presenting. So I actually have two laptops open, and I'm going through the PowerPoint into them. One's for Discord presenting, one's for recording. So leftmost and rightmost derivations, they're simple ways of approximating ambiguity. So if they result in the same word via different expansions, so if their pass-throughs look different, then that would mean the context-free grammar is ambiguous. Even if their pass-throughs are identical, that doesn't, however, mean that there exist other pass-throughs that are not identical for the same word. So there could still exist several different pass-throughs for the same word. So this might mean it's valid to say that differently passed leftmost and rightmost derivations implies that the context-free grammar is ambiguous, because false implies anything. So if we do the leftmost and rightmost derivations and they happen to have different pass-throughs, or if we can visualize like the how they're passed, If they are different, then we know that the grammar is ambiguous. If they're the same, then the grammar might either be ambiguous or not ambiguous. So it's a quick way of testing whether it's ambiguous, if that makes sense. Finally, what's Chomsky normal form got to do with any of this? So if a word is attempted to be derived algorithmically, then it'll have a certain complexity. So the CFG could be very large or it could be small. It approximately depends on the sizes of V and sigma in the tuple. So the number of variables and the number of terminals. If the number of productions, so expansions, which is the number of it is denoted the cardinality of R, which is 2 lines. We learned that in MLFCS. The number of productions might be a lot, but algorithmically, if the productions themselves aren't very large, then it's relatively easy computationally. So that's just an example of what cardinality is, but I think you all know that. If a single production expands into it expands one variable into several variables or terminals at once. So if like A expands into AA, BA, BC, etc., then there might be a large runtime for a single expansion. In Chomsky normal form, the context-free grammar might have a large number of productions and a large number of variables, but the number of terminals won't have changed. However, in Chomsky normal form, each of the expansions is very small. We can only expand a variable into a single terminal or 2 variables. So, yeah, it says that here. So this means that because the productions themselves are quite small, deriving a word algorithmically is quite easy in Chomsky normal form. The total number of steps, I'm not going to prove that here, but as a general rule, the total number of steps to derive a word from a context-free grammar in Chomsky normal form is 2n minus 1, where n is the length of the word, so the number of terminals that we want to end up with. This is linear, ON. So it means that no matter what the complexity of derivation is for other alterations of context-free grammar, in Chomsky normal form, it's always 2n minus 1, so it's relatively efficient. That is everything. It's done.